Hi boys and girls. Today's lecture 6.2 is entitled The Natural Logarithmic Function Integration, and this will be part 1 of that discussion. Now that we have spent time differentiating the logarithmic function, it is time to turn our attention to integration of the natural logarithmic function. The differentiation rules that we were using, d dx of natural log of x equals 1 over x, and d dx of natural log of u is equal to u prime over u, produce the following integration rule. Let f be a differentiable function of x, then the integral of 1 over x dx is natural log of x plus c, and the integral of 1 over u du will be natural log of u plus c. This, of course, should not be surprising. If the derivative of natural log of x was 1 over x, then the integral of 1 over x should give us the natural log of x. Because du is u prime dx, the second formula can also be written this way. U prime over u dx is equal to the natural log of u plus c. Let's try a couple of examples. In this first example, I'm going to rewrite the integral taking the constant 2 to the outside of the integral. That way, I'll be able to easily see that I'm actually being asked to integrate 1 over x dx, which of course is natural log of x. So this integral will be 2 natural log of x plus c. Now the reason we put absolute value bars around the argument of the natural log function, of course, is that there is this domain restriction. X has to be greater than 0. So make sure that when you're stating your answer that you have indicated that the argument will remain positive by putting absolute value bars around the argument of the logarithmic function. Looking at this second example, I want to remind you that when the denominator is not just a simple x, but a function of x, we're going to be looking for what is called a du over u pattern, where the denominator will be u. If u is 4x minus 1, then du is 4 dx. Notice that I have the 4x minus 1 in the denominator, but my numerator is not 4 dx. You can always manipulate the integrand by inserting a constant, as long as you compensate for that by putting the reciprocal of that constant on the outside of the integral. So I'm going to rewrite this now, putting a 4 dx in the numerator over 4x minus 1, and I'll compensate for that by putting 1/4 on the outside of the integral. Now I do have the du over u pattern, and so that means this is the natural log integral. It will be 1 over 4 times the natural log of 4x minus 1 plus c. In this example, we're going to use the log rule to find area under a curve. Our directions are: find the area of the region bounded by the graph of y equals x over x squared plus 1, the x-axis, and the line x equals 3. As you can see, I've included a diagram of that region here: the curve x over x squared plus 1, the x-axis, and the line x equals 3. Now, I did not need a left boundary because at 0 the curve crosses the x-axis, so 0 will be my left endpoint of integration. We know that this definite integral from 0 to 3 of x over x squared plus 1 dx will yield this area. So now I look to see if I have the natural log pattern. I need du over u. Well, that means if u is x squared plus 1, then what I would need in the numerator is 2x dx. I have the x, and it's a good thing because you can't insert a variable into the integrand, but you can insert a constant, and that's what I'm going to need to do. For this to be the accurate derivative of x squared plus 1, this should be 2x dx, which means I'll compensate for inserting that 2 by putting a 1/2 on the outside. Now this is a du over u pattern, and the integral of du over u is natural log of u. Of course, our u in this case is x squared plus 1. So this is going to be, and I'll come down here, 1/2 times the natural log of x squared plus 1. and of course we'll be integrating from 0 to 3. Now you'll notice that I didn't put absolute value bars around x squared plus 1 to make this point. This number is always going to be positive. Whatever you're putting in for x and squaring it is positive, and adding 1 to it will also mean that it's positive. So I have no worries that this could somehow accidentally become negative, and I don't need to insert the absolute value bars there. All right, let's go ahead and evaluate this integral. This is going to be 1/2 times natural log of 3 squared plus 1, which is 10, minus natural log of 0 squared plus 1, which is 1, natural log of 1, which will be 1/2 natural log of 10 minus 0, since this goes to 0, and that is this decimal approximation. 1.151 is approximately the area under the curve from 0 to 3. In using the log rule for integration, the trick is to become adept at recognizing the du over u pattern in the integrand. So let's practice with these few examples doing just that. As I look at this quotient, I'm going to suggest that u would need to be x cubed plus x. Then that means du would be 3x squared plus 1, which is exactly what I have in the numerator. So this is already set up to be du over u. That means that the integral is the natural log of u, the denominator, x cubed plus x, plus c. Usually there are slight adjustments that need to be made, but occasionally you have the exact du already in the numerator. Now let's look at letter B. If u is tan x, du is secant squared x. Oh, by the way, this was 3x squared plus 1 dx. So once again, we have du over u in the integrand, and that pattern is the natural log of u. So this will be natural log of tan x plus c. That's supposed to be in tan. Now let's look at letter C. If u is equal to x squared plus 2x, then du would be 2x plus 2 dx. And that's not what we have in the numerator, but closer inspection will reveal it could be what we have in the numerator if we multiplied this numerator by 2 and compensated for inserting that 2 by adding a 1/2 on the outside of the integral. Now this is a du over u pattern, which means our integral will be 1/2 natural log of x squared plus 2x plus c. And in our final example, once again, if u is the denominator, 3x plus 2, du would be 3 dx. Well, the 3 is not there, so we will need to insert it. I will just morph this 1 into a 3 and compensate by putting a 1/3 on the outside of the integral. Now this is du over u, and therefore our integral will be 1/3 natural log of 3x plus 2 plus c. Integrals to which the log rule can be applied often appear in disguised form. What? For instance, if a rational function has a numerator of degree greater than or equal to that of the denominator, long division may be needed to reveal the true form of the integrand. Here's what we're being asked to integrate, and if this is not a du over u pattern, we really have no way of taking this integral. So let's see if it is a du over u pattern. If u is x squared plus 1, du would be 2x dx. That is definitely not what we have in the numerator. But technically, this rational expression is improper. The degree of the numerator is greater than or equal to the degree of the denominator. Long division will help simplify this rational expression and give us an integrand that we are able to work with. So let's go off to the side and do a little bit of polynomial long division. X squared plus 1 is the divisor, and x squared plus x plus 1 is the dividend. Look at the first terms. X squared goes into x squared once, and when we multiply 1 by this divisor, we get x squared plus 1. Draw the line and change both of these signs because we need to subtract these terms from the dividend. The x squareds cancel, we bring the x down, the 1's cancel as well. So this quotient is 1 plus x over x squared plus 1. Now let's rewrite our integral with our reduced rational expression and attempt to take the integral again. This will be the integral of 1 plus x over x squared plus 1 dx. And of course we can separate this into the integral 1 dx plus the integral x over x squared plus 1 dx. This integral becomes x, and once again we take a look at the rational expression to see if it's a du over u pattern. Well, remember when u was x squared plus 1, du was 2x dx. We have the x, but the 2 is not there, so let's insert it and compensate for that insertion by placing 1/2 on the outside of the integral. Now this is a du over u pattern, and we'll integrate accordingly. 1/2 natural log of, again, x squared plus 1 will always be positive, so we don't need the absolute value bars, plus c. Who knew there would be a day where we would say, long division to the rescue? Here's another instance in which the log rule pattern is disguised. We're going to use a change of variables technique, which will allow us to rewrite the integrand so that the log rule may be used. As we examine this integrand, we can see that it is definitely not your typical du over u pattern. Even if we decided to FOIL out this denominator, x squared plus 2x plus 1, we could see that if this is our u, this is still not completely our du. So let's try another technique, a radical technique, substituting these variables for another. I'm going to say that u will be x plus 1. Usually when you're using this technique, you let u be the more complicated part of the integrand, and in this case that's x plus 1. Of course that means du is dx, because the derivative of x plus 1 is just 1 dx. We also need to solve for x here, and that means x will be u minus 1. Now let's rewrite this entire integrand, replacing everywhere that we see an x or a dx with our u substitutions. So now my integrand will be 2 times x, which is u minus 1, over x plus 1 squared, u squared, and then dx was du. So now this is the integral. I'm going to take the 2 on the outside of the integral, and that will give me u minus 1 over u squared. Now that my denominator is a monomial expression rather than a binomial expression squared, I can separate this into 2 fractions. So this will be 2 times the integral of u over u squared minus 1 over u squared. Let's simplify a bit. This is going to be 2 times the integral of 1 over u du minus 2, distributing the 2, times the integral of u to the negative 2 du. Well, this is the natural log pattern, and we'll be able to use the power rule for this integrand. So continuing to simplify, this will be 2 natural log of u, and then for this integral, adding 1 to negative 2 gives us negative 1, and dividing by that negative 1 will give us a positive 2 here, plus 2u to the negative 1, and then rewriting this will give me 2 natural log of u plus 2 over u plus c. Now let's replace u with the original substitution for our final answer. This will be 2 natural log of x plus 1 plus 2 over x plus 1 plus c. That's it for today's lecture. Learning the du over u pattern should be helpful in interpreting this integral. God bless you, boys and girls.